Our last section for Unit 1 is improper integrals. So, two types of improper integrals. One of them has infinite limits of integration. So that you're going to rewrite as a limit as t approaches infinity. The other type of improper integral is when there is a vertical asymptote within the interval over which you are integrating, and that you're going to write as a limit as t approaches wherever that asymptote is. Okay, so type 1, this is the type where you have an infinite limit of integration over infinite intervals. So you either write it as the limit as t approaches positive or negative infinity, or you may have to divide it into two pieces if it's going both ways. Improper integrals are called convergent if they have an answer, divergent if they do not. And again, if it goes both ways, they have to both be convergent or it's divergent. And there's the pretty picture. If it decreases quickly enough, then you can get an answer for the area underneath the curve, is basically how you can think of it. So let's look at an example. Step number 1, write it as a limit. So example 1, we want to look at the limit from 1 to infinity, 1 over x dx. So limit, and t is just what I'm using. You could use b, you could use k, whatever you want to. Approaches infinity, integral from 1 to t, 1 over x dx. Make that a little bigger and see if I can get it to focus. That's better. Okay, so now limit stays just like it is. We do the integral of 1 over x dx. That's the natural log of the absolute value of x from 1 to t. It's a definite integral. We plug in our bottom, our top minus our bottom. Limit as t approaches infinity. Natural log. Don't really need the absolute value because you know t is getting bigger and bigger. It's positive. Minus the natural log of 1, but I know that's 0, so I'm just looking at the limit as t approaches infinity of the natural log of t, and that's infinity. Natural log grows slowly, but it does continue to grow forever and ever and ever. So this one diverges. There's the pretty answer. So if you see 1 over x, it has an infinite area. 1 over x squared, it decreases a lot more rapidly, so it has a finite area. Let's look at another example. Example 2, we want the integral this time from negative infinity to 0 of x e to the x. So, step number 1, write it as a limit. Limit as t approaches negative infinity of integral from t to 0 x e to the x dx. Now we've been practicing all these different integration techniques. One of them was integration by parts, which is exactly what we need for this. So we let u be equal to x, then du is dx. We let dv be equal to e to the x. So v is e to the x. So I'm going to go ahead and move down here, give myself plenty of room to groove. Limit as t approaches negative infinity. Integral from t to 0. Actually, I need to do my u times v first. So let's put this u times v, so x e to the x evaluated from t to 0 minus the integral from t to 0 of v du, so just e to the x dx equals limit as t approaches negative infinity, x e to the x minus e to the x evaluated from t to 0. I'm going to copy it over on the other side of my paper and start again. So I copied my limit just like it was on the other side of the paper, just so I wouldn't forget. And then I went ahead and plugged in 0 and t. Remember, we were looking at this evaluated from t to 0, so I plugged the 0 in first. So this is 0 minus 1. I have the limit as t approaches negative infinity minus 1. I'm going to divide it into pieces because I have the limit as t approaches negative infinity of t e to the t, and then I have plus the limit as t approaches negative infinity of e to the t. So, limit as t approaches negative infinity of e to the t. Let's think about what e to the t looks like. It looks like that. So as t approaches infinity, this piece approaches 0. This piece is negative 1. Now I need to look at this piece, and just looking at that limit, I'll come down here, limit as t approaches negative infinity, t e to the t. Well, as t approaches negative infinity, t goes to negative infinity, but e to the t goes to 0. So I have an indeterminate form, but it's not ready for L'Hopital. So I can rewrite this limit as t approaches infinity, and I'll put LH there for L'Hopital. Actually, no, I'm going to rewrite it first and then use L'Hopital because it's not L'Hopital ready. Limit as t approaches infinity, I'm going to write it as t over e to the negative t. That makes it easy. Now, as t approaches negative infinity, t on top goes to negative infinity, but e to the negative t looks like that. So as t approaches negative infinity, this would be negative infinity over infinity. So now I can L'Hopital this thing, and I have the limit as t approaches negative infinity of 1 over negative e to the negative t. Big bottoms do indeed go to 0. Move that out of the way. So this piece goes to 0, and this one is a convergent integral. Now, let's look at our pretty answers here. Exact same thing. 0, minus 1, 0, and 0. Another example. integral from negative infinity to infinity. So we did one that went from a number to infinity. We did one that went from negative infinity to a number. Now we have one that's going from negative infinity to positive infinity. So I'm going to have to divide this into two limits. So this is going to be the limit as t approaches negative infinity. Now you can choose anything that you want to divide it. I'm going to divide it at 0 just because that makes sense to me. So from t to 0 of 1 over 1 plus x squared dx plus the limit as t approaches positive infinity, 0 to t of 1 over 1 plus x squared dx. Alrighty, so limit as t approaches negative infinity. Oh, 1 over 1 plus x squared is arctan. So this is going to be inverse tangent of x from t to 0 plus the limit as t approaches infinity, inverse tangent of x. From 0 to t. The limit as t approaches negative infinity, I put 0 in first, inverse tan of 0 minus inverse tan of t plus limit as t approaches infinity, inverse tangent of t minus inverse tangent of 0. Again, I need to go to another sheet of paper, so I'll take a second and write it down. All I've done so far is to plug in inverse tangent of 0 is 0, inverse tangent, of 0 is still 0. Now, what does inverse tangent look like? Well, it looks like that. Because remember, in order for tangent to have an inverse, we have to limit its domain to go from negative pi halves to pi halves, and tangent has vertical asymptotes at negative pi halves and pi halves. For inverse tangent, we revolve that around the identity line, so we end up with horizontal asymptotes at pi over 2 and negative pi over 2. So as t approaches negative infinity, we have 0 minus negative pi over 2 plus, as t approaches positive infinity, pi over 2 minus 0. So pi over 2 plus pi over 2, I don't even need a whole nother row to write down pi. Easy enough. That one converges to pi. Okay, now it's your turn to practice. So see what happens. Limit as the integral from 1 to infinity of 1 over x to the third power. We'll meet back and compare answers. How'd it go? Step number 1, write it as a limit. Step number 2, integrate. Step number 3, plug in the limits of integration. Step number 4, calculate the limit. And since this one, your t stays down in the denominator, big bottoms go to 0, you end up with just a half. Because 1 over x cubed decreases really quickly. Let's look at practice number 2. This time we have 1 over the square root of x. Meet me back here. How'd that one go? Very similar. It was still just to add 1 to the exponent, divide by the new exponent kind of integration. But this time when we added 1 to the exponent, it brought that variable up above the fraction bar, so my integral diverged. Let's look at, oh, this one's different. We have an exponential function, but the base isn't e. How unusual. You're going to have to remember how to integrate that. So maybe you had to open up that last PowerPoint from when we did the strategies for integrating and remind yourself what the integral of a base rather than e to the x is. It's just the exact same thing divided by the natural log of the base, just like the derivative would have been 2 to the r times the natural log of the base. And then we plug in 2 to the 0 is equal to 0, it's equal to 1 over the natural log of 2. And 2 to the t looks pretty much like e to the t. So as t approaches negative infinity, 2 to the t approaches 0, and 0 over natural log of 2 is still 0, so we end up with just 1 over the natural log of 2. Oh, we have one where we get to do, and no, we do not need to do a integration by parts. Practice. We'll meet back and compare answers. So at first glance, I thought I had a product here and I was going to get to do integration by parts. But no, it's just a straight out u substitution problem. I let u be equal to the exponent of e. du is negative sine of theta d theta, so that became negative e to the u du. And I updated my limits of integration. And now I look at the limit as t approaches infinity, negative e to the cosine of t. Well, the limit as t approaches infinity of cosine of t does not exist. So the limit as e raised to this power doesn't exist. So this integral diverges. That one was a little different. Okay, so example 4 kind of refers us back to these practice number 1 and 2 that we did here. So we notice practice number 1, when we had x cubed in the denominator, we got a nice friendly answer. Practice number 2, when we had x to the 1/2 in the denominator, it diverged. So you can think about what you think the answer to this question is going to be. For what values of p is that integral convergent? Also thinking way back to our very first example that we did, number 1, where we had 1 over x, and we ended up with just looking at the natural log. There's example 1. I had gotten lost in my papers. But remember, if we had just 1 over x and the integral from 1 to infinity, it was divergent. So make a prediction and then we'll look at it. I'm just going to calculate this integral with the p in it. So just like always, step number 1, write it as a limit. Limit as t approaches infinity, and we're going from 1 to t, and I'm going to write this as x to the minus p dx. So this is the limit as t approaches infinity. Add 1 to the exponent, divide by the new exponent. From 1 to t. Plug in t. Limit as t approaches infinity. t to the negative p plus 1 over negative p plus 1 minus 1 over negative p plus 1. Now, we need to ask ourselves, when does this limit exist? Well, it exists if it has a big enough bottom to go to 0. Remember, this is the limit as t approaches infinity, and as long as we have t to the negative p plus 1 living above the fraction bar, it's going to go to infinity. If t is below the fraction bar, then it's going to go to 0. So let's write that down. If t is above the fraction bar, and what does that exponent need to look like for it to be above the fraction bar? Then diverges. If t is below the fraction bar, then that limit is equal to 0. So, in order for it to be below the fraction bar, negative p plus 1 needs to be less than 0, not 1. Because if it's positive, it lives above the fraction bar. If it's negative, it lives below the fraction bar. So, negative p is less than negative 1. So p needs to be greater than 1 for the integral to converge. Because then this piece will go to 0 and you'll be left with just the minus 1 over minus 1 plus p. So if p is a big number, that means that when you add 1 to the exponent and divide by the new exponent, your t is still below that fraction bar. So there it is in a nice blue box, which makes it official. The integral from 1 to infinity of 1 over x to the p is convergent if your p is bigger than 1, and divergent if p is less than or equal to 1. Let's switch over to type 2 integrals. This time we have perfectly normal looking limits of integration, but we have a vertical asymptote living somewhere inside of our interval. It could be at the end, or it could be in the middle. So it has a discontinuity. It could have a discontinuity at the right end, at the left end, or you could have to divide it into pieces if the asymptote is in the middle of the interval. And convergence and divergence works exactly the same. If you get an answer, it's convergent. If you don't, it's divergent. Let's look at example 5. We have the integral from 2 to 5, 1 over square root of x minus 2 dx. Now, if you don't think about it hard enough, you may think, oh, that's easy. It's just a fundamental theorem of calculus. Take the antiderivative and plug in the endpoints. Nuh-uh, because if you plug 2 into this, you have a vertical asymptote. That makes this an improper integral. So you have to do a limit. You've got a bad guy. 2 is your bad guy. So I usually go ahead and write down my interval so I can remind myself which sided limit I have. I have the limit as t approaches 2 from the right, and we're going from t to 5, and I'm going to write this as x minus 2 to the minus 1/2 power dx. The limit as t approaches 2 from the right. We can't approach 2 from the left because you can't plug numbers into that radical that are less than 2. So we have add 1 to the exponent, divide by the new exponent. If you need to let u equal, you can, but this one's simple enough. I'm just going to write it as x minus 2 to the 1/2 divided by 1/2 evaluated from t to 5. Limit as t approaches 2 from the right. I plug 5 in, I get 2 times the square root of 5 minus 2 minus 2 times the square root of t minus 2. As t approaches 2 from the right, I end up with 2 times the square root of 3 minus 2 minus 2 is 0, so just 2 times the square root of 3. Pretty answer, there it is. So it's convergent, and there's the pretty picture. This is when it gets close enough to that vertical asymptote fast enough that it limits the amount of area in there, and you can calculate it. Let's determine whether one or secant of x from 0 to pi halves. So example 6. We're looking at the integral from 0 to pi over 2, and now let's think about what secant is. Secant is 1 over cosine. So my bad guy is not 0 because I can plug 0 in there, but at pi halves, secant has a vertical asymptote. Secant actually looks like, kind of looks like a parabola, but it's shooting off towards infinity right there at pi halves, because cosine is equal to 0 there at pi halves. So we have the limit as t approaches pi halves, and this time it's from the left. Integral from 0 to t of secant of x. So this is the limit as t approaches pi halves from the left, natural log, absolute value, secant plus tangent, evaluated from 0 to t. So limit as t approaches pi halves from the left, natural log, I'm going to run out of room here, secant of t plus tangent of t minus natural log of secant of 0 plus tangent of 0. I'm going to get a new sheet of paper. So I just rewrote the first part, and then I plugged in 0 to secant tangent. Secant of 0 is 1, tangent of 0 is 0, so that's the natural log of 1. So that part's just 0. Now I look at the limit as t approaches pi halves of secant plus tangent. Well, tangent of pi halves is, let's see, sine over cosine, so that doesn't exist at pi halves. I can't plug pi halves into secant either, so this whole thing would be taking the natural log of things that are approaching infinity. This thing diverges. And there's the pretty answer. Let's look at another one. Now, this one we're going from 0 to 3. And again, it looks like that's not hard. It's just the natural log of x minus 1. Why can't I just do it? Well, you got a bad guy. The bad guy lives there at 1. Now, if it says evaluate if possible or determine if it converges or diverges, that's going to be a hint to you that you have an improper integral. But always check for bad guys when you have a rational expression like that. So we have the integral from 0 to t, and the limit as t approaches 1, because my bad guy is at 1. So let's make our little interval here. We're going from 0, 1, and 3. So we're approaching 1 from the left of, and I'm going to go ahead and write it as x minus 1 to the minus 1 power. Doesn't really matter. We already know it's natural log. Limit as t approaches 1 from the right, and we go from t to 3 of x minus 1 to the minus 1 dx. So, even though we have two limits, it's really easy because we only are integrating once. We're integrating the same thing twice. We have the limit as t approaches 1 from the left, natural log absolute value of x minus 1, evaluated from 0 to t, plus limit as t approaches 1 from the right, natural log absolute value x minus 1, evaluated from t to 3. We plug in our limits of integration. Equals limit as t approaches 1 from the left. I have the natural log absolute value t minus 1 minus natural log of the absolute value of 0 minus 1. I'm going to go ahead and put this on another line because I write really big. Limit as t approaches 1 from the right, natural log absolute value of 3 minus 1 minus the natural log absolute value of t minus 1. Okay, so the limit as t approaches 1 means what's inside here is approaching 0. So this is going down to negative infinity, because remember what natural log looks like. As natural log approaches 0, the graph approaches negative infinity, so this thing diverges. As soon as one thing diverges, you get to quit. That piece is going to diverge, go down to negative infinity as well. Okay, example 8. Natural log from 0 to 1. What's wrong with this guy? Well, we just said as x approaches 0, natural log is going down to negative infinity. So we're going to have to write this one. And we're going from 0 to 1. 0 is the bad guy, so it's going to be the limit as t approaches 0 from the right, integral from t to 1, natural log of x dx, which is the limit as t approaches 0 from the right. Natural log, oh boy. Now this is one where we have to go back and do our integration by parts. So u is equal to ln of x. So du is 1 over x. dv is equal to dx. So v is equal to x. Maybe you have this one memorized. If you do, that's fine. I'm just going to go through the integration by parts real quick. So I have u times v, x, ln of x, evaluated from t to 1, minus the integral from t to 1, v du, x cancels with x. That just gives me dx. So this is equal to the limit as t approaches 0 from the right of x ln x minus x evaluated from t to 1. Limit as t approaches 0 from the right of 1 times the natural log of 1 minus 1 minus t ln of t minus t. Well, 1 times the natural log of 1, that's 0. That's negative 1. That's 0. This is the only troublesome thing. So far, I have just a minus 1 for my answer. Let's look at the limit as t approaches 0 from the right of t times the natural log of t. Oh no, I have an indeterminate form because this is 0 times negative infinity. So we'll rewrite this one as limit as t approaches 0 from the right, natural log of t over 1 over t. That was one of those little tricks we learned back when we were learning L'Hopital's rule. Now what we have is negative infinity over infinity, and that's something that L'Hopital can deal with for me. So this is the limit as t approaches 0 from the right. Derivative of the numerator is 1 over t. Derivative of the denominator is minus t to the minus 2 power, because it's just the derivative of t to the minus 1 power. So let's rewrite this. This is the limit as t approaches 0 from the right. I have a t that's really living down below the fraction bar, but I have 2 t's that should be above the fraction bar. So I have negative t squared over t, which is the limit as t approaches 0 from the right of t, which is 0. So my final answer is just negative 1. How'd it go? So initially I forgot about my minus sign here. It's really easy to add 1 to the exponent and divide by the new exponent. But don't forget, if u is equal to 5 minus x, then du is minus dx. So I put a minus sign in front here, add 1 to the exponent, divide by the new exponent, and it becomes a plug and chug. Not bad. Try practice number 6. Where's your bad guy? Your bad guy's at 1. Okay, I admit it. I knew what the answer was, but my drawing of arc sine was not good. So we talked about what the bad guy was. It's at 1. So I have the limit as t approaches 1 from the left. Arc sine 0 to t. So limit as t approaches 1 from the left, and I'll bring the pretty Desmos picture over to show you. So as we approach 1 from the left, arc sine approaches pi halves. So because we know that arc sine of 1, sine of pi halves is equal to 1, so the arc sine of 1 is pi halves, and it only exists as you approach from the left because we have to limit that domain in order for sine to have an inverse function. So that one was pretty easy to calculate. Let's see what number 7 has. Okay, number 7 doesn't just jump right out at me and tell me that it has a bad guy. Let's look at practice number 7. We have the integral from 0 to 4. So if there are any zeros of x squared minus x minus 2 between 0 and 4, then we got a bad guy. Otherwise, we just have to partial fraction decompose. So this would be equal to x minus 2 times x plus 1. So I have a bad guy. This denominator is equal to 0 when x minus 2 is equal to 0. So when x equals 2. There's my bad guy. Duh. So we'll divide it into 2 pieces, give it a try, we'll come back and compare answers. Okay, so we figured out where our bad guy was, so I wrote it in 2 pieces, and then I went ahead and just wrote my integrand down and did the partial fraction decomposition, and then I integrated and I ended up with 2 logs. I went ahead and plugged in t and 0 and 4 and t. So these pieces are okay because I have the natural log of 2, natural log of 1 is 0, natural log of 2, natural log of 5. Those are all good. I could plug this in and I would have 1/3 natural log of 2 plus 1, but as t approaches 2, I'm trying to take the natural log of 0, so this thing diverges. Because as soon as one little piece of it diverges, the whole darn thing diverges. So that is improper integrals. Infinite limits of integration and bad guys or vertical asymptotes within your interval. Those are the 2 types. You can do it. That's it. You know everything you need for test 1.